Today I'm going to talk to you about periodic trends. We started some of this in class. So starting with atomic radius. How big are atoms, basically, is this trend. If you go down a column in the periodic table, so starting with hydrogen, going down to francium, for example, do the atoms get bigger or smaller? Well, as we go down a column, we're adding more and more shells, going from n equals 1 to 2 to 3 to 4. And those shells keep getting bigger and bigger as n increases. And so the atoms also will be getting bigger and bigger as those electrons are further and further out. So the atomic radius increases because there's more and more shells. What about if we go from left to right? So for example, going from potassium across to krypton. Now we're in the same shell the whole time. You might think that it gets bigger and bigger because we're adding more and more electrons, and electrons repel each other. But on the other hand, there's more and more protons. You can see we go from 19 on up to 36. And of course, the electrons are attracted to the protons, and so you have a larger and larger positive pull as you go from left to right, and that means that the atomic radius will decrease because more protons, more positive charge, pulling in those negative electrons more closely. So then, let's look at an example. Compare cesium with scandium with strontium. Which one will be the largest and which will be the smallest? Well, let's see. Cesium is down here, so we're thinking it's big because it has more shells than the others. It's also furthest to the left, so it doesn't have as many protons as if you go across its own row, and so it will be big for that reason as well. Strontium is going to be smaller because it's up and to the right, and scandium is going to be even smaller because it's further up and further to the right. So the smallest of all will be scandium, then strontium, and then cesium. Scandium, strontium, cesium. So smallest is scandium, middle strontium, largest is cesium. Overall for this trend, smallest atom of all is going to be helium because it's up and to the right. The largest atom of all is going to be francium because it has many shells and it's to the left. Next trend, ionization energy. So this one is how much energy does it take to strip off the outermost electron in an atom. So for example, you could take a helium atom and hit it with maybe a cathode ray or something and strip off its electron, leaving behind Ag+, and then the E- comes off. But that takes some energy. And what is that change in energy? Again, that's considered going down a column first. So if we're going down a column, how much energy does it take to remove an electron? So remember, again, we're adding shells, so the electrons we're adding as we go down are further and further from the nucleus. So it's like we're going from Mercury, Venus, Earth, all the way out to Pluto way out here, right? This furthest out electron. Easiest to pick off because it's so far from that attractive nucleus. So the ionization energy decreases because the outermost electron is further and further away. How about if we go from left to right? So if we're in a row, we're in the same shell again. But again, similar to atomic radius, we have more and more protons holding those electrons more and more tightly as we go from left to right. And so it's going to be more and more difficult to pull that electron away. It's going to take more and more energy. So the ionization energy will increase as we go from left to right because there are more and more protons to attract those electrons. So let's look at an example. Let's compare boron, calcium, oxygen. Well, let's see. Oxygen and boron are on the top, but oxygen's to the right. So that's going to have more protons. It's going to require more energy than boron. And then boron versus calcium. Well, calcium's to the left and it's down. So you're going to have fewer protons attracting it compared to others in its own row, and it's further down, so it's a further out shell. So calcium will require the least, then boron, and then oxygen. Oxygen will require the most energy to remove its electrons. So to sum up this ionization trend, the upper right-hand corner here will be the largest, most difficult to take an electron from helium because it's on top and to the right. And the smallest will be down here at francium because it's at the bottom and it's to the left. Okay, this next one, electron affinity, is kind of the opposite of ionization energy. What is the energy change for adding an extra electron? So, for example, if we had a neutral helium atom, and this time we added on one extra electron to make helium minus, what is the change in enthalpy for this reaction? That change in enthalpy is called the electron affinity. So let's think about what we'd expect as we go down a column again. As we go down a column, would the atoms want the electron more and more, or would they want the electron less and less? Think about that a minute. Maybe pause the video. Do the atoms want the electron more and more, or less and less? In fact, the elements would want the electrons less and less as we go down a column, because the extra added electron is going to be in a further and further out shell, further from the nucleus. So the electron affinity is less and less negative. The delta H is less and less negative. What's confusing sometimes about this trend is, mathematically speaking, then technically the electron affinity is increasing because it's becoming less and less negative. But we usually don't talk about it that way. We'll just say that the electron affinity is less and less negative as we go from top to bottom. We won't mention that it's increasing. It's just less and less negative. All right, from left to right, what would you expect? Do the elements want the electron more and more, or less and less as we go from left to right? Okay, remember there's more and more protons, so you got more and more positive pull on those electrons, and so the atoms want the electron more and more. So we have a more and more negative electron affinity, which technically is decreasing, but we'll just say more and more negative. So let's do an example. Oh wait, there's an exception. As you go from left to right, the atoms want the electrons more and more, but not when you get all the way to the right. Once you get to the noble gases, they don't want the electron at all. And so the delta H, the electron affinity, jumps back up and becomes less negative all of a sudden when you get to this last column. So this trend only works until you get to the halogens, and then it jumps back up again. So let's compare fluorine with lithium and rubidium. Who wants the electron the least? Well, it's going to be the rubidium. It's going to want it the least. Rubidium will want it the least because it's to the left and it's down. Lithium will want it more than that because at least it's closer in the shell. Fluorine will want it more than lithium because it's further to the right with the more protons. So the most negative, the one that wants it the most, will be the fluorine, then the lithium, and then the rubidium will be the least negative. Really doesn't want that electron as much at all. And in fact, if you look at the numbers, you can see here fluorine is negative 328 kilojoules per mole. That's energy released, exothermic, when that extra electron is added. Lithium, you add that extra electron, it's way less, negative 60 kilojoules per mole. And rubidium, even less, negative 47 kilojoules per mole. And when I mean less here, I mean less negative. But if you think about the math, negative 328 is a lower number than negative 60, which is a lower number than negative 47. So that can be confusing. Most negative is fluorine, and a more negative number is technically a lower number. To sum up this trend, The upper right-hand corner is going to be the most negative, except that should actually be on fluorine, not helium. Fluorine wants the electron the most, and francium wants that extra electron the least. All right, bonus concept for you. This is not a trend so much, but it's related to the trends. So we talk about it here. Ionic radius. What is the radius of a species with the same electron configuration? So let me explain what I'm talking about with an example. So here we have F minus, Ne neutral, and Na plus. All of these, if you think about it, have 10 electrons because fluorine starts with 9, but if you go to F minus, then it has an extra one, so it becomes 10, like neon. Sodium, similarly, starts with 11, but if you go to Na plus, you're losing one, so you're going back to 10. So these all have 10 electrons. So the electron configuration is going to be all the same if we build them up, starting with the lowest orbital, 1s2, 2s2, 2p6. They all have the exact same electron cloud as neon, 1s2, 2s2, 2p6. Same exact electron cloud. But the only difference is fluorine only has 9 protons, neon has 10, sodium has 11. So the question then, which one is going to be the smallest and which one's going to be the biggest? Okay, so like we said, the electron cloud's the same. But sodium has more protons, more positive, so that's going to be a greater pull on that electron cloud. So sodium's going to be the smallest, followed by neon, followed by fluorine. Sodium's the smallest, it has 11 protons. Neon's next with 10, and fluorine's going to be the largest because it has 9. All right, that's it for periodic trends, and we are now finished with Chapter 8. We'll talk about Chapter 9 next.